Hi there. Um, Today's lesson, we're going to delve into the idea of implicit differentiation. Okay, so far most functions have been written in explicit form. Like we can isolate y and there's only x on the other side. So y equals 3x squared minus 5. Again, the variable y is explicitly written as a function of x. Um, the function xy equals 1 is written implicitly. What we can do is simply write it explicitly by solving for y and then differentiating, okay? So like we could write that as y equals 1 over x. Now y is in terms of x, and we can go from there. But sometimes it's difficult or even impossible to write a function explicitly. So for example, let's say that you have x squared plus 2, or sorry, xy, x squared minus 2y cubed plus 4y equals 2. If we tried to isolate this y, notice that we would end up with kind of a problem, right? So we would either have, we would still have y, we would have strange radicals involving y, like it's not going to work out. So to find the derivative of y with respect to x, to find dy dx, we would use something called implicit differentiation, okay? So to understand how to find this dy dx, this derivative of y with respect to x implicitly, we have to understand that the differentiating is taking place with respect to x. Okay, so when we're differentiating terms involving x alone, which is what we've been doing, we differentiate as usual. But when we have terms involving y, we use the chain rule because we're assuming that y is defined implicitly as a function of x. So again, this may seem silly at first, but it can be helpful and sometimes necessary at times, okay? You don't have to write that down, okay? All right, so let's just kind of look at this, all right? This is asking us to differentiate with respect to x. That's what that d dx is. That's saying take the derivative of me, okay, with respect to x. And notice here when we have the derivative with respect to x of x cubed, that the variables match. The derivative operator, like that's really the bottom part here. This is the derivative operator. Okay. Anyway, so like that derivative operator matches the variable that we're dealing with. And so what's happening is we're really taking, in this case, we're really taking 3x squared dx dx. Okay, we're really taking the derivative of, like, anyway, we're doing dx dx, and that dx dx is really just 1. So when they match, we don't have to worry about this because that just turns into 1 and we end up with 3x squared. But notice here, we're taking the derivative with respect to x of y cubed. Here, these variables disagree. So what we can do is we can apply the chain rule. So we're going to take 3 times y squared using that power rule. But now we're differentiating with respect to x. So now this is dy dx. And that's differentiating with respect to x. Okay. In letter C, we have the derivative with respect to x of x plus 3y. So we can think about applying that to each term. So we're going to have the derivative with respect to x of x. And then using our derivative rules, we can pull out that scalar multiplier of 3 times the derivative with respect to x of y. Okay. Notice that these match. So in a sense, we're going to just basically say dx dx, which is 1. but then here these disagree. So that means that we've got to keep that dy dx present. So that would be what we end up with here. If we're taking the derivative with respect to x of xy squared, we're going to have to use the product rule. So we know that we can take x times the derivative with respect to x of y squared plus y squared times the derivative with respect to x of x. So basically we're using our product rule there. And then we can differentiate as normal. So we're going to then apply the chain rule here essentially. So we're going to take the x, but now we're going to differentiate y squared with respect to x. So we can use the power rule. That leaves us with 2y, but since these disagree, we still have dy dx. Here we have y squared, and then we have the derivative of x with respect to x. That's just 1. So you could clean it up a little bit and write like 2xy dy dx plus y squared. And that would be a way to do that, okay? So this seems like a little dumb right now, I totally get it. But this becomes necessary when we're trying to differentiate certain functions, which of course we're going to do next. But these are the guidelines for the implicit differentiation and how you use them. First, you're going to differentiate both sides of the equation with respect to x. Then what we'll do is we'll take all the terms that have dy dx on the left side of the equation, and then we'll move all the other terms to the right side of the equation. Then we'll factor dy dx out of the left side and then isolate the dy dx by dividing by all the, so that's the way we do implicit differentiation. So let's take a look with this super fun example. We're going to find dy dx given y cubed plus y squared minus 5y minus x squared equals -4. This is basically saying to solve for this, we want to find dy dx. So essentially what we'll do is we are going to take the derivative with respect to x of each side. Again, you know me, I'm going to be a little dramatic. So I'm going to take the derivative with respect to x of y cubed plus y squared minus 5y minus x squared. And then the same thing over here, the derivative with respect to x of -4. So I'm taking the derivative with respect to x of both sides. So now let's keep in mind what we were saying and evaluate these different, like basically take the derivative of each term. Okay, so when we do that, we end up with 3y, but these don't match. Oh, sorry, 3y squared, but these don't match, dy dx. Taking the derivative with respect to x of y squared, that's going to give us 2y dy dx, because those don't match. Here, this would be minus 5 dy dx. And then here we have minus 2x. And again, like you could think about it as dx dx, but the dx dx cancels, okay? That's why we haven't seen it before, because we've been dealing with taking derivatives with respect to x of x, okay? Anyway, and then on the other side, we know that when we take the derivative with respect to x of a constant, that's going to give us 0, okay? So again, this dx dx is just cancel, and that gives us 1. So notice that all of these terms have dy dx in them. So we'll keep all of these on the left, and we're going to move this guy over to the right-hand side. And then maybe what we could do also, do you guys mind if I factor out the dy dx right away? What step was that? Or was that a separate step? No, okay. So this is our step one, is differentiate, okay? I'll keep it separate here. So now I'm just gonna have all my terms involving dy dx on one side. And then all the other terms on the right side, okay? The third step is to factor out the dy dx from each of those terms. So I've got y squared plus 2y minus 5. Okay. And then step 4 is to isolate dy dx. And obviously that's a factor, so we're going to divide by 3y squared plus 2y minus 5. And now what we've done is we have solved implicitly for dy dx, okay? This is a little different in the past because all of our equations have been in explicit form. We've only had x in our derivative. Notice that here dy dx has both x and y terms. Okay, that's new. So that's kind of exciting. Okay, so our dy dx will often have, in this case, both our x and y terms. And that's kind of what happens when we do that implicit differentiation. Okay. The graph is here also. We can see from the graph that y is not a function of x. All right. However, the derivative does give the formula for the slope of the tangent line at any point on the curve. It's just that we would have to know both x and y in order for us to do that. So a couple little notes. It is meaningless to solve dy dx in an equation that has no solution points. So if you had something like x squared plus y squared equals -4, yes, that looks like an equation, but let's think about it. That's a circle with a radius that's not there. So this is something that's impossible. So it would be silly for us to differentiate this, even implicitly. But there might be some graphs or some equations that have some places that are not differentiable, but if a segment of the graph can be represented by a differentiable function, even if it's just a segment of the graph that can be represented by the differentiable function, then dy dx will have meaning as the slope at each point on the segment, okay? So even if the whole graph on its own isn't differentiable, if there's a segment of it that is, then you can, apply this for that specific segment. Remember that a function is not differentiable. I'll use a different color for that because it's a different story. That a function is not differentiable at points with vertical tangents, at points where the function is not continuous, or if it's like a singular point. So for example, if we look at example 2, like if I were to pop up there again, do you see that there's a vertical tangent at x equals 1? Okay, I'll just make this little note. So at x equals 1 and x equals -1, there are vertical tangents. And so that's going to be at -1, 1 it looks like, and at 1, 1. And if you substitute that into dy dx, if you substitute that in, you're going to get something over 0, which is an issue, okay? So even though there are some places that it's not differentiable, you're still able to calculate the slope at the points where it does work, okay? So again, this was just looking in example 2. There are some points where that doesn't work out, but any points where it can is legal, all right? Okay, so example 3 says, if possible, represent y as a differentiable function of x. And if I look at letter A, I have x squared plus y squared equals 0. Well, we can see that this is a circle, but with a radius of 0. So what does that mean about the graph? If it's a circle with a radius of 0, that means that your graph is a single point. Like it's just like, whoop, There you go, like that's it. So because of that, what that tells us is that this is not differentiable. So see how they said if possible? Okay, so that one would not be differentiable. Let's think about letter B though. Letter B, we have x squared plus y squared equals 1. And so we know that this is going to be a circle with a radius of 1. I'm going to try to draw a circle, okay? And so that means that any vertical tangents are going to be an issue there, right? So we have vertical tangents at -1 and at 1. So notice that we have vertical tangents at x equals -1 and x equals +1. So what that means is that technically you could separate this into two pieces. So we could have two pieces where like we have the top part of the function and then the bottom part of the function. So if we tried to do that here, we have y squared equals 1 minus x squared. And then we could take the square root of that. So that's going to be y equals plus or minus the square root of 1 minus x squared. And so those are two different pieces. So one of our pieces is that y is the positive square root of 1 minus x squared. But let's think about when that's true. That's only going to be this top part of the graph, right? So again, so that's on -1 to 1. And then this is going to be this bottom part of the graph, again on -1 to 1. So this would be a way for us to represent that as something that was differentiable. Now, the reason that we didn't include 1, I know that our graph goes like from -1 to 1 and includes it, but we did not include it because it's not differentiable at 1, okay? So I'll say it this way, that we excluded -1 and 1 since it's not differentiable. Why is that word so long? So it's not differentiable at x equals plus or minus 1, okay? So let's let's do the same thing for something like letter C. In letter C, I have x plus y squared equals 1. You could also write that as y squared equals the opposite of the quantity x minus 1. When we think about what this looks like, is that this is going to be a parabola. It's a y squared parabola, so it's going to open either left or right. This tells us it's going to open left, and it's going to basically have its vertex there at 1, 0. But based on our knowledge of graphs, it's going to look something like this. Okay. However, if we start dissecting that a little bit, what we see is there's going to be a vertical tangent here, again at x equals 1, okay? So that means that we could think about this as, we'll do this one. So I'm going to rewrite this as y squared just equals -x plus 1. It was just like this so we could tell where the vertex was, okay? We could tell where our HK was. So essentially that means that y is going to be plus or minus the square root of, I'll write 1 minus x so that the x is negative to be in front, okay? And what we want to do is exclude 1. So what we can do is we can say that y is going to be equal to the positive square root of 1 minus x. So notice that goes from -infinity to 1. And then y is the opposite of 1 minus x. It's going to be the lower half, also from -infinity to 1. So Usually what we would do is we would just say that y equals plus or minus the square root of 1 minus x, right? The problem is that they're asking us to make sure that every point is differentiable. And so when if they were to ask, which I don't see a ton to be honest, but if they ask you to find the places where it's differentiable, you just rewrite it and exclude any points that are not differentiable, okay? But let's get back to implicit differentiation because that's a little more exciting in my opinion. So example 4 wants you to determine the slope of the tangent line to the graph of x squared plus 4y squared equals 4. Again, when it tells us here to determine the slope of the tangent line, this is asking you to find dy dx. So let's differentiate both sides with respect to x. So I'm going to differentiate, how small do I have to write here? I'm going to differentiate the left side, x squared plus 4y squared with respect to x, and differentiate the right side, which is 4, with respect to x. Okay. So now from here, what I can do is I can apply, basically the differentiation rules. So with respect to x, if I take the derivative of x squared with respect to x, that's like 2x dx dx, which again, we don't worry about because those match. Plus, do you guys agree that using the power rule, that would be 8y, but since these don't match, that would be dy dx. And then equals the derivative of constant with respect to x is 0. Okay. Now this is the only term involving dy dx, which means that we can just plop the 2x over to the other side by subtracting. And then I could divide by 8y to isolate the dy dx. And I have that dy dx is negative 2x over 8y. But you guys would probably simplify that, right? Just divide by 2. So our best answer would be to have it reduced, that dy dx is the opposite of x over 4y, okay? Let's keep going. That's really my favorite thing to do, are the things like example 2 and 4 as far as the implicit differentiation. Okay, example 5, find the slope of 3 times the quantity x squared plus y squared equals 100xy at 3, 1. Well, if it's asking us to find the slope, once again, this is asking us to find dy dx. So that means that we're going to basically take the derivative of the left and the derivative of the right with respect to x. Now, one thing is that, I don't know if you noticed this or not, but on this side, on the left-hand side, we're going to have to use the chain. Oh, I forgot the squared. Okay. That because we have x squared plus y squared quantity squared, that means that we're going to have to apply the chain rule. Okay. Notice that we have an inside function, like is this x squared plus y squared, and then the outside function is the idea of something being squared. So we're going to have to apply the chain rule to that first. And then notice that on this side we have 100xy, that this one we're going to have to use the product rule, that we're going to deal with x, because 100 is a constant, so we don't worry about it, but we deal with x and we deal with y. Okay? So let's differentiate each of those sides. All right, so at first, I'm going to just pull this constant out. I have 3. And so then using the chain rule, then I'm going to have 2 times x squared plus y squared, basically to the first power. and then chain rule still kind of new. So times the derivative with respect to x of the inside function, which is the x squared plus y squared. Okay. Do you want to just deal with that for a minute? Okay. So again, this was our outside function. And then this was our inside function that we're still dealing with. Okay. So now what I can do is, let's see. I could distribute this if I wanted to. We'll just finish the other side. Okay, so we're going to pull the 100 out here. And then if I use the product rule, that means that I'm going to want to take x times the derivative of y with respect to x plus y times the derivative of x with respect to x. Okay. So notice that we have each piece and then the derivative of each one as well. Okay. Okay, sorry. All right, so we're gonna have, so then we'll go back to the left side. So this is all multiplication that's over here. So I could multiply this 3 times 2 to make 6. And then I still have this x squared plus y squared. I don't need to the first power. But now I need to differentiate x squared plus y squared with respect to x. So let's think about what that becomes. I'll kind of color code that here. So this would become 2x dx dx, which we don't write, plus 2y dy dx, which we do have to write since those don't match. Okay. Next over here, this ends up being 100. And then this is x times dy dx plus y essentially times 1, right? Because the derivative of x with respect to x is just 1. You want me to put that? There you go. Okay. So now maybe let's distribute a little bit. Okay, so let's distribute. I'm going to take this whole thing. This is kind of where it gets a little clunky. I'm going to take this whole thing and distribute it to the 2x and to this term. That's essentially what we're doing, all right? So when I multiply that here, I get 12x, x squared plus y squared, plus 12y, x squared plus y squared times dy dx. And then over here, just trying to get rid of some of the parentheses, I have 100x dy dx plus 100y. So here, this one side was a little easier. I was just distributing the 100 to each part. Okay. So remember we said we want all the terms involving dy dx on one side. These are the terms that are involving dy dx. So I want all of those on one side. So I can have 12y x squared plus y squared dy dx. Now I'll move this guy over, minus 100x dy dx. And then I still have 100y on this side. Now I need to move this term that didn't have a dy dx term over. So 100y minus 12x times the quantity x squared plus y squared. Okay. Then essentially I need to pull a dy dx out of there. And so if I pull a dy dx out, I'm left with 12y x squared plus y squared minus 100x, and then that equals the 100y minus 12x x squared plus y squared. So then dividing, I have 100y minus 12x times x squared plus y squared all over 12y times x squared plus y squared minus 100x. It's really cute, isn't it? All right. Before I happy cloud my answer, I looked. You guys see that there are 4 terms that are involved in this expression. The 100y, the negative 12x times the quantity x squared plus y squared, the 12y times the quantity x squared plus y squared, and the negative 100x. If they have any common factors, technically we should reduce. So do you see that we can divide by 4 here? We can divide by 4. And so then a simplified answer for dy dx ends up being 25y minus 3x times the quantity x squared plus y squared all over 3y x squared plus y squared minus 25x. Okay. And so here is my derivative, an expression for the derivative. So if you were asked to differentiate, use implicit differentiation, that would be what you do. All right. They did, however, ask us to evaluate at a specific point. It did ask us to evaluate at 3, 1. So now we're going to evaluate at the point 3, 1. So then we just put those values in. So dy dx is going to be 25 times 1 minus 3 times 3, times 3 squared plus 1 squared all over 3 times y, which is 1 times 3 squared plus 1 squared minus 25 times 3. And then we just evaluate that. So that's going to be 25. 3 squared plus 1 squared is going to be 10 times 9 is 90. So 25 minus 90. Again, this is 10 times 3, which is 30, minus 75. So that gives me negative 65 over negative 45. And we can divide each of those by negative 5. And that gives me 13/9. Okay, so the moral of the story, I have nowhere to write, is that that the derivative of y with respect to x, or the slope, is going to be 13/9 at that point 3, 1. Remember, it's not always 13/9. That's just the slope at that specific point. So don't write so big, I guess. Okay. All right, almost done with this part, okay? The next thing we'll do is just, again, find the equation for the slope of x squared plus y squared minus 4x, that whole quantity squared, sorry, equals 2 times the quantity x squared plus y squared, again, providing it exists. So we're going to differentiate each side, and now that we've got the gist of that, I don't need you to necessarily write that anymore. But we are going to differentiate, but because we have this quantity squared, we're going to use the chain rule again. This is our inside function, x squared plus y squared minus 4x. And then the idea of the outside function is that something squared. Okay. So if I am differentiating with respect to x, I end up with 2 times x squared plus y squared minus 4x. And then we want the derivative with respect to x of x squared plus y squared minus 4x. Again, that was to the first power. Okay, so this was the idea of my outside function, and this is what I'm dealing with, that inside function. Okay, and now if we take the derivative on the other side, this is just to the first power, so we're good. So this is just going to be 2. And then I can take the derivative of x squared plus y squared with respect to x. So that's going to be 2x dx dx, which is 1, and then plus 2y dy dx, which is not 1, so we should write it. All right. So now let's take the derivative here. So I've got still 2 times x squared plus y squared minus 4x. Now I want the derivative of x squared plus y squared minus 4x with respect to x. So this is good, these match, so 2x, except now this is going to end up being 2y dy dx, and then this would just be minus 4. Okay, that's nice. And then we end up having, to deal with terms, so I'll just distribute this here to create some new terms. So 4x, and then plus 4y dy dx. All right. So again, I want to try to find the dy dx terms. Instead of distributing everything, just think about taking this whole thing, okay, the 2 times the quantity x squared plus y squared minus 4x, and let's distribute it to the 2x, to the 2y dy dx, and to the negative 4. It just ends up being a little bit better. So then we have 4x, x squared plus y squared minus 4x. Now I have plus 4y times the quantity x squared plus y squared minus 4x dy dx minus, and then this ends up being 8 x squared plus y squared minus 4x. Okay, and here I'll just leave this alone still. All right. So now we want all the terms involving dy dx on one side. So notice that this term and this term have dy dx. So these can all go on the left-hand side. So 4y x squared plus 4y minus 4x dy dx minus 4y dy dx. And then on this side, we still have 4x, and we have to bring these guys over. So minus 4x times x squared plus y squared minus 4x. Now to bring this over, that would be plus 8 times x squared plus y squared minus 4x, that quantity. Okay. So on the left, I think it's pretty intuitive that we would factor out the dy dx. And we would be left with 4y times x squared plus y squared minus 4x minus 4y. Okay, so we're just taking the dy dx out of each of those, equals. And then I don't know if you guys notice this or not, but do you see that these two have like a common factor in them? And just like if you had like 2x plus 5x, you would turn that into 7x. We can factor this negative 4 plus 8 out of there if we want. And so I'm going to do that. So I'm going to have 4x, and then combining these terms together, I'm going to have negative, I'll say 4x minus 8. Is okay with that? And then times x squared plus y squared minus 4x. Okay. So now we want to find dy dx. So our dy dx is going to be this whole thing. And then I notice again that I could pull a 4 out of here. So maybe I'll do that. So I have 4x and then minus 4 times x minus the quantity x minus 2 times the quantity x squared plus y squared minus 4x. Of course, I don't know what that is. Okay. And then over this 4y times x squared plus y squared minus 4x minus 4y. So that's one way we can do that. Again, if I look at each term, do you see that each term, 1, 2, 3, 4. Each of those is divisible by 4. That must be the lucky number. If you're 18, you should go play the lottery. I'm kidding. So we can divide each of those by 4. And that ends up being x, and then just minus x minus 2 times x squared plus y squared minus 4x, all over, divide 4 out of here, y times x squared plus y squared minus 4x, and then minus y. So there are a lot of ways that you can write this. I don't know what I would want to do in a test situation. But for example, like in the denominator, you could factor out a y there too. And so you could write y times x squared plus y squared minus 4x minus 1 if you wanted. So a lot of different possibilities. So there are other ways that you could write it. Just make sure, like if you were doing an AP exam and this was multiple choice, just make sure that your answer can get to that piece. Okay. That I think is all I want to do. Hang on. Okay, yeah. We didn't differentiate anything with the trig, but I mean, you do it the same way. Okay, so we'll save that for next time. But that is a little bit about implicit differentiation. So next time we'll practice a little bit with the trig, but also talk about how it might ask us to write our final answer in terms of only x or only y or both. Okay, so that's it. Have a great one.